All right, welcome back again, everybody. Today we're moving on to section 1.2. We're going to talk about some important number sets. We're going to talk about division, and then I've got some really cool visualizations of rational numbers versus irrational numbers to show you at the end. So let me go ahead and get started. I'll pull up the slides. All right. So first, an overview. We're first going to talk about just the natural numbers. And what we're going to do is we're going to build up the entire real line as we go along. So first, we've got the natural numbers. Then we're going to talk about the integers and a little bit of some number theory. Then we're going to talk about a very important theorem, the fundamental theorem of arithmetic. The general rule in math is if a theorem is called the fundamental theorem of something, then you better know it. Make sure you know what those fundamental theorems are. Then we're going to talk about rational numbers, and in particular, Euclid's division lemma and the division algorithm. We're going to go over the division algorithm because we will see that again throughout the course, and we're going to use it in meaningful ways. Then we'll talk about irrational numbers, and finally, just the set of real numbers. All right? Okay, so let's start with the natural numbers. So the set of natural numbers is denoted by this fancy n, and it is the set 1, 2, 3, 4, 5, dot, dot, dot. That means it keeps going forever. These are what we call the counting numbers. These are the most natural numbers, the ones you can count on your fingers, right? That's what they are. There's infinitely many of them, but that's how they progress 1, 2, 3, 4, 5, and beyond. If we include zero in this list, many books will call this new set the set of whole numbers. So the set of whole numbers is basically all of the natural numbers, but you include zero as well. And in this class, we'll use n sub zero to denote the whole numbers, the natural numbers with zero tossed in. Okay. Now the set of integers is denoted by this fancy z. That's because the German word for integer starts with z. So the integers are all of the positive natural numbers and their opposites and zero. That's what they are. So the integers are basically all the counting numbers plus their additive inverses, meaning the negatives of those numbers, right? Just like so. One thing I want to point out, notice that the set of whole numbers is contained inside the set of integers. So the integers contain the set of whole numbers. So in a naive sense, the integers is a larger set. Funny enough, it actually turns out that they have the same size, but that's when infinity gets involved and it gets really cool and pretty wild. You'll talk about that later on. Now that we know what the natural numbers are and the integers are, we can start to build up a number line to represent them. So what I've got down here, let me zoom in a little bit, is just a geometric representation of the integers on a number line. So here's zero, kind of right in the middle, one, two, three, four, and beyond. Negative one, negative two, negative three, negative four, and beyond in the negative direction. And that is the set of integers pictured as a number line, although it's not quite a line yet, right? All right. Now that we have the integers, we need to talk a little bit about what factors and divisors are. We need to do a little bit of number theory just to kind of refresh your memory, or if you haven't seen this stuff, to introduce you to this vocabulary and these words that we use to describe these things. So first, let's talk about factors. So factors are simply parts of a product. That's it. So when you hear the word factor and we say, oh, what are the factors of that number? What we mean is, what are the parts of that product? So here's two examples. 12 is 3 times 4. So 3 and 4 are factors of 12. Those two numbers are factors of 12. How about this? Maybe this will remind you of something from algebra. Maybe you twinge a little bit seeing it. Don't worry, we're going to review this stuff when we get into chapter 3. But if we take this polynomial here, this quadratic expression, and we factor it into these x plus 1 times x plus 2, right? And if you multiply those together, you get this back. Okay, so these are two factors of this expression. So x plus 1 and x plus 2 are factors of x plus 1 times x plus 2. So that's what a factor is, parts of a product. If your factor is not 0, then we can also call it a divisor. And we say that a number n is divisible by a number a if there's some number b such that n equals a times b, or in other words, a is a factor of n. Okay, now I just said a lot of stuff, so let's pause for a minute. And what I want you to do is I want you to read, oops, wait, not that. I wanted this. There you go. I want you to read this paragraph in your head for a minute. Okay, now what I want you to do is I want you to say something out loud about this paragraph that you just read. Remember, you don't need to say it to somebody. It can be to nothing. It can be to your computer screen or your dog or your friend. Maybe you're watching the lecture with your friends. You can say something to them. Give your brain that feedback. Okay, what I wanted to point out specifically is this relationship here. We say n is divisible by a number a if there's a number b such that n equals a times b. So in other words, we can say that a is a factor of n. And we can also say that A divides N, and we can say N is divisible by A. There's all of these equivalent ways of saying the same thing. But when we say that N is divisible by A, we mean you can find a B such that A times B equals N. That's what it means. Okay, now let's talk about prime numbers versus composite numbers. These play an important role in number theory, a huge role in number theory, still an active area of research to this day. So a prime number p is a natural number greater than 1 whose only integer factors are 1 and p itself. That's a prime number. So in other words, if you tried to factor the number p, the only way you could possibly do it is 1 times p. That's a prime number. And those are very, very special numbers, as we'll see because of the fundamental theorem of arithmetic. Now, a composite number is like a not that. So a composite number is a natural number that is not prime. Um, Maybe more specifically, I could say, or maybe more intuitively, I could say, composite numbers have a whole bunch of factors, or they could have more than just one and themselves, right? So, like 4 is not a prime number because 4 is 2 times 2. 6 is not a prime number because 6 is 2 times 3. You can write the number 6 in more ways than just 1 times 6, right? Compare that to prime numbers. Here's a prime number 2. The only way you can factor 2 is 1 and 2. In fact, 2 is the only even prime number. 3 is also a prime number. 13 is a prime number because you can't factor it into other factors than just 1 and 13. There you go. Um, so one of the interesting things is that the set of natural numbers, and in some sense, an extension sense, the integers, those sets are partitioned into the set of primes and the set of composite numbers. So in other words, if you've got a natural number, it's either prime or it's composite. That's what I mean. The prime numbers partition the natural numbers into two sets, the prime numbers and the not prime numbers. So here's a question for you, and I want you to try this one on your own. Is the number 30 prime or composite? And if it is composite, then I want you to list all of its integer factors, okay? So think about this one for a second, right? And now I want you to say something out loud to yourself to give your brain that feedback. You could even just repeat what the sentence says. Right. Now I want you to try to work it out. So try to factor the number 30 if it's I'm sorry, if it's composite. See if you can come up with all of the natural number factors of 30. And then we'll do it together in a moment. Right. Okay. So 30 is not prime. I can tell that right away just because I'm thinking of like 3 times 10, right? 3 times 10, that's not 1 times 30. So it's definitely not a prime number. So let's see what all of its integer factors are, or positive integer factors. Yeah, there you go. So it can't be prime. Now, there's a bunch of factors of this number: 1, 2, 3, 5, 6, 10, 15, 30. All of these numbers divide the number 30. Okay. They're all factors of 30, and they're all factors because, for example, you can write 30 as 1 times 30, or 2 times 15, or 3 times 10, or 5 times 6. Here's four different ways of factoring the number 30. And these little things here, these are what we call factor pairs. So if you ever hear that phrase, factor pairs, it means come up with a pair of numbers that multiply to give you the number 30. That's a factor pair. Okay, now we get to the fundamental theorem of arithmetic. And this is a critical fundamental theorem. And it says this: every integer greater than 1 can be factored into a product of prime numbers. Moreover, the factorization is unique up to the ordering of the factors. Okay, this is a very powerful result. It says no matter what natural number you've got, it can be factored into a product of primes or powers of primes. If you remember exponentiation, so if you've got multiple factors that are the same, like 2 times 2 times 2 times 2, you can list those individually, or you could group them together as, like, 2 to the fourth, for example. But no matter what, every natural number can be factored into a product of prime numbers, and that factorization is unique for that number, except maybe reordering the factors, like switching them around, moving them around. Now, when you factor a number into its prime factors, that's called its prime factorization, which makes sense, right? Call it a prime factorization. Okay, now I want you to try this. This might remind you of what you did way back in grade school, finding prime factorizations of numbers. So what I want you to do here is I want you to try to find the prime factorization of 504. All right, so think about it for a moment. Okay, now say something out loud about the problem to yourself, to no one, to anyone. And now try to work it out on your own. So come up with a product of prime numbers that equals 504. I'll give you a little hint. Try doing a factor tree, if that rings a bell. Okay, now let's do it together. We're going to make a factor tree. So maybe this will ring a bell from when you were younger. You can basically start by writing the number 504 at the top, and you can factor it into a factor pair. You can factor it into a product of two numbers that multiply to be the number above. Um, I like to go for the low-hanging fruit. So if a number is even, like 504, I just divide it by 2, and that's my first factorization. So 2 times 252. And then I keep going. 252 is also even, so I'll divide it by 2 again. 2 times 126. 126 is also even, so 2 times 63. All right, now I'm finally at the first non-even number, but 63 is one of those multiplication facts that they make you memorize back in grade school, right? 63 is 9 times 7. 7 is prime. 9 is not prime because 9 is 3 times 3, so we can factor it again to get 3 times 3. Now, all the circled numbers here, those are the prime factors of the number 504. So the prime factorization is just the product of all of those prime numbers. 2 times 2 times 2 times 3 times 3 times 7. Or using exponent notation, 2 to the third times 3 to the 2 times 7. This is the prime factorization of 504. There you go. And that's basically an application of the fundamental theorem of arithmetic. You can factor that number 504 into this prime factorization, and that's the only way you can do it, except for maybe moving these factors around and like putting them in different places, but that is it. And the only prime factors are 2, 3, and 7, plus powers of those numbers. Okay. Um, Oh, this is kind of what I just basically what I just said. So the fundamental theorem of arithmetic says every one of these positive integers greater than 1 can be factored in this way. Um, for a prime number p, the factorization is just the number p itself. So the prime factorization of 13 is just 13, since it's prime already. The prime factorization of 223 is just 223 because it's prime already. Now, Here's the catch, and maybe you kind of feel this when you try to do it yourself. The fundamental theorem of arithmetic guarantees the existence of a prime factorization, but producing the actual factorization can be extremely difficult. Yeah, it can be really, really difficult, especially if the number is huge. Imagine the most gigantic number you could imagine, and then try to factor it, and try to factor it. So. These days, in modern math and science, we typically rely on computers to find these types of factorizations. And developing efficient computational methods to do so is an active field of mathematical research today. People still try to find better methods for factoring integers. Okay. So, computer science majors, this one's for you. I want you to check out the Wikipedia page for integer factorization and just skim it. It's going to be way over your head, maybe, but just skim it so you can get a taste of what's going on today, right? Coming up with these factorization algorithms is hard, but it's also a fun exercise, and we've already got a lot of them, and they're all differently efficient, I will say. Some are very efficient, some are not. If you can come up with another one, you'll get a prize. I'll say it like that. um, yeah, so read about some common algorithms. Keep these ideas, the stuff like the fundamental theorem of arithmetic, the idea of primeness and prime factorizations and composite numbers. I want you to keep those ideas in mind when we study polynomials, because there's an intimate connection between these structures, which we'll talk about in chapter 3. Okay, moving along. Now let's talk about the rational numbers. So people figured out pretty early on in human existence that not every number is an integer. There are obviously quantities in between the whole numbers, right? So for example, or just for example, like one half or three fourths. You can cut things into pieces that are not whole numbers. So people figured out a few thousand years ago how to at least partially formalize this idea of in between numbers and how to relate it to integers in a consistent way, right? Because if we want to talk about a number between like 4 and 5, how can we make sense of that? How can we explain it, right? So let's take a look at this. So remember, these are the natural numbers here. These are the integers. But if in my little picture here, if you kind of zoom in, there's a bit of gray in there, right? It's like we're missing some numbers in this construction of the number line that we're going for. And some of those numbers are called rational numbers. So how do we define the rational numbers? Well, first we denote the rational numbers, the set, by that fancy Q. The way that I like to write it is draw an O and then kind of swoop the side and then cut down like that, like a Q. So that letter represents the set of rational numbers. And what is the set of rational numbers? It's every number that can be represented in this form, A over B, where A and B are integers and B is not zero, not dividing by zero here. All right. One thing I want to point out is that A and B do have to be integers. They can't be irrational numbers. They can't be like pi or square root of 2 or something. A and B need to be integers. So in essence, Q is just the set of all ratios of integers where the denominator is not zero. So here are some examples. These are all rational numbers. Negative one half, three fourths, 1,734 over 201. Four can be written as a rational number, as we're going to see in a moment here. You just divide it by one and you got a rational number. Um, Here's one, negative 83 over 6,790. These are what rational numbers look like, and they could be messier than that, but that's a good start. Um, yeah, I already mentioned this, but for a number to be rational, the numerator and the denominator both need to be integers. They have to be like positive or negative counting numbers, and b cannot be zero. Also note that every integer can be written in this form. You just make the denominator 1, right? So for example, 4 is 4 divided by 1, negative 2 is negative 2 divided by 1, 0 is 0 divided by 1. So what that means is that the rational numbers, the set of rational numbers contains the set of integers as well. Okay? So there's like a containment going on, right? One set is inside of another set's inside of that one, and it goes on, right? So in some sense, The rational numbers are basically filling in some of the gaps in the real line, but not as many of the gaps as you might think. Let's take a look at our updated line. Here we go. So we had natural numbers first, then we had the integers second, kind of going the other direction or other direction. Now the rational numbers are kind of going dit, 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 dit in between all those. There you go. So these are representing the rational numbers, also these big dots, because remember, every one of these integers is a rational number. It's a rational number. So we're getting there, kind of filling in the gaps, but oops, there you go. But not filling them in as much as you might think. We'll delve into that a little more now, but also later. Um, so here's an important interpretation, right? A rational number is the result you get when you divide one integer by another integer. We can use our fundamental intuition to produce an important characterization of rational numbers. We're going to see this throughout the course, and this is what I would say a critical understanding about rational numbers. So remember that A over B is how many times B fits into A, or it's how many B's fit into A. And I like to give this example. It's a simple one. 3 over 2 is 1.5, right? Well, since every rational number is either an integer or it lies in between two integers, we can use this fundamental intuition of our fundamental intuition of addition, and we can write every rational number as an integer plus a fractional part. So think about that for a second. Let me throw up the thinker and I'll say it again. Every rational number can be written as an integer, or it can be written as an integer plus a fractional piece that's smaller than one, right? So again, like 1.5, if I zoom in here, right? One, or this number here, which is actually 3/2. Oops. We can write that as an integer plus a fractional piece. We can write it as 1 plus 1/2. And even more intuitively, this 1/2 is the distance is the distance from that lower integer. There it is. So what is a rational number? It's basically an integer plus a fractional part, right? Or it's just a straight integer. The fractional part may be zero. But those are the boring rational numbers. Those are just integers, right? So when we write a rational number in this form, it's often called a mixed numeral, or maybe less accurately, a mixed number. You probably heard about these in the past. Do not be afraid to use mixed numbers. I know a lot of students, oops, I forgot to turn off the thinker. I'm sure you're still thinking though. Um, uh, the, a lot of students feel like they're not allowed to use mixed numbers, but I want to tell you right out, you absolutely can and you should. And oftentimes, writing things as a mixed numeral is more intuitive and makes more sense and reveals more structure than writing everything as a quote improper fraction, right? You know, I always like to use cooking as an example because I like to cook. But if you like 11 over 3. Okay, what if you needed 11 thirds cups of something or teaspoons when you're cooking? Is it easier to think of it as 11 over 3, or is it easier to think of it as 3 and 2 thirds? So like three wholes and then 2 thirds, right? So do not be afraid to use mixed numerals. They're totally allowed. Help yourself. And we're actually going to do it a lot later on. Okay. So this thing that we're doing here, where we're writing every rational number as an integer plus a fractional part, this is actually a result of something called Euclid's division lemma, or Euclid's division theorem, and it results from what's called the Euclidean division algorithm. This is the division algorithm that you learned back in grade school. Maybe you hated it. I know I hated it a lot back when I learned it. If we have time, I would love to show you a more efficient division algorithm, or at least a more intuitive division algorithm called the expanded algorithm. But just know that there is an algorithm out there called the division algorithm, and we're going to learn it here again today and throughout the course. There's actually a lot of division algorithms. There's not just one or two, there's a whole bunch, and they end up being equivalent to the Euclidean division algorithm. If you're interested in reading about them, just follow that link. But the processes can be very different. They will give you the same thing, but the processes can be different. Computer science majors, once again, I encourage you to check out that link because programming such algorithms is a fun exercise. Okay, so let's look at this division lemma and see how the division algorithm gives us this. This is where things are going to start to get a bit technical. So take a deep breath. Okay, let any of your anxiety just wash away. We're going to see this a lot throughout the course. We're going to make sense of it. We're going to learn it together, okay? Here we go. Let a and b be integers, and we're going to suppose that b is not 0. Then there exist unique integers q and r, such that we can rewrite a over b as q plus r over b. Or in other words, equivalently, we could write this same equation as a equals b times q plus r, okay? And we also have the fact that r is greater than or equal to 0, and it's less than b in size, less than the absolute value of b. Okay, now before I get to the rest, I want you to just stare at this and think about it for a minute. Maybe read it in your head for a moment. Okay, now try to say it out loud to yourself and try to phrase it in your own words. Just kind of say this how you would say it to yourself just naturally, right? All right. Okay. Now let's read the rest of it because now we have some vocabulary. This bottom little paragraph here is all the vocabulary that goes along with this interpretation. A over B is the ratio, like we saw in the previous section. A is what we call the dividend. B is called the divisor. B is like the thing doing the division in some sense. Q is called the quotient. R is called the remainder. And R over B is called the fractional part. Okay, the fractional part. Now, before we move on and do an example, I want to show you how these two things are equivalent. You basically just multiply both sides by b. So I want you to try this for a second here. If we multiply both sides by b, oops, sorry, right? The b's here will cancel. You'll be left with a. And then this b is going to distribute to those two terms. We're going to see this more throughout the course. So that's where we're getting the b times q. And then again, R over B times B, the B's cancel and you're left with R. So again, R is called the remainder. So when you do the division process, when you do the division algorithm, sometimes you'll get a remainder, sometimes you won't. If you don't get a remainder, then hey, A must be an integer, right? And here, B is a factor of A. So there's that stuff we were talking about just a minute ago, right? If you do end up with a remainder, the remainder is R, and that means you're going to have a fractional part, okay? Let's practice one, okay? Let's write 79 over 4 in the form Q plus R over B as a mixed numeral. And this is one I definitely want you to try on your own. So just think about it for a sec. You might already know how to do this, and you're like, boom, I got it. Okay, say something out loud to yourself about what you're going to try. What division algorithm are you going to use? Okay, and now I want you to try it on your own. Basically, do that division. Divide 79 by 4 in whatever way you know how, and write it in the form of a mixed numeral. All right, now let's do it together. Here we go. Um, this is the standard division algorithm. This is the standard Euclidean division algorithm. However you want to do it, you are welcome to do it. Okay. This one is just with numbers. It's pretty straightforward. How many times does 4 go into 7? It goes in there once. So we put a 1 up here. And then we subtract 4 from 7. We're now taking care of the tens place. So subtract 4 from 7, you get 3. Bring down the 9, you get 39. Then you repeat it. See, that's why it's an algorithm. It's like a loop, right? You repeat the process. Now, how many times does 4 go into 39? Let me count. 4, 8, right? Okay, it goes in there 9 times, right? Okay, so 4 times 9 is 36. Now we subtract. 39 minus 36 is 3. How many times does 4 go into 3? We're trying to repeat the algorithm now. Oh, 4 doesn't go into 3, right? You cannot fit 4 into 3. So, or at least not a whole time, right? So we've got a remainder. So we can say that 79 divided by 4 is 19, remainder 3. Now, Euclid's division lemma says, hey, that means we can write 79 over 4 as 19 plus 3/4. So because we have a non-zero remainder, we're going to have a fractional bit. This number cannot be an integer. It's got to be like a purely rational number in some sense. So the quotient is 19. The remainder is 3. So the fractional part is 3 over 4. Thus, 79 over 4 can be written as 19 plus 3/4. And a lot of times we'll denote it like this in the form of a mixed numeral. Okay, now I want to show you like a geometric picture of this, okay? So if you plot this on a number line, you can see the number 19 and 3/4 is 3/4 away from the whole number 19. Let me zoom in, right? Here's all of our whole numbers. 79 divided by 4, we got 19 plus a fractional piece, 1, 2, 3/4. Here we go. Notice I'm dividing this segment into 4 equal-sized pieces. 1, 2, 3, 4. And I'm taking 3 of those pieces. 1, 2, 3. Boom. Just like that. All right. Oops. Come on. Okay. All right. So here's the thing. I kind of mentioned this before. If the remainder is 0, then a over b just equals q, and the rational number is just an integer. For example, 36 divided by 9 is just 4. The remainder is 0. Okay. Um, it's precisely when r is not 0 that a non-integer rational number is produced. For example, 36 over 7 gives you 5 plus 1/7. So in a sense we're going to see later on, R over B contains all of the fractional information of that number. If R over B is 0, then your number is not, it's just an integer, right? But if R is not 0, then you have a fractional bit. You got like a little bit left over there, okay? Now, more specifically, this number here, this fractional part, tells you exactly how different the rational number a over b is from the whole integer part. So this is an important interpretation. So remember that picture of the number line I just showed and so on. But r over b is how different the rational number is from its whole integer part. And that's specifically because here, think about this equation, right? Subtract q from both sides. Move q over there. And what you get is r over b is equal to a over b minus q. And that's a difference, right? Like we talked about in the previous section, that's the difference. So the difference between this rational number a over b and its integer part is exactly this fractional part. That fractional part contains all that information there. So for example, 19 and 3/4 minus 19 gives you 3/4. That's the fractional part, the difference between the two. Okay, now, we've talked a lot about rational numbers, but that's not all the numbers there are. People also figured out a few thousand years ago that not every number is rational, that there are these numbers that you can write in ways that are not a ratio of two integers, right? Famously, the Pythagoreans discovered this. And perhaps the most famous irrational number is the number square root of 2. And it was discovered by a disciple of Pythagoras to be irrational. Other famous examples of irrational numbers include pi and e, and phi is another one we'll see. And this result was actually really, really shocking. But it was ultimately correct, and it yielded another new set of numbers that are called the irrational numbers. So simply put, the set of irrational numbers is the set of all real numbers that are not rational. Not rational. That's pretty much it. So basically, you've got, if you're talking about real numbers, you've got rational numbers and not rational numbers, the irrationals. Okay. Now, putting those two sets together gives you what we call the real numbers, the real number system, the set of real numbers. So we denote this with a fancy R. I usually write this as two vertical lines, and then I swoop the loop of the R like that. So whenever you see that symbol, we mean the set of all real numbers, rational numbers irrational numbers, the integers are included in there, the whole numbers are included in there, the natural numbers are included in there, all of them, right? So including the irrationals, um, with the rational numbers and using a standard notion of distance, like how far apart things are, that completes the real line. The irrational numbers are what fill in all the other gaps left by the rational numbers. And now our picture is complete. There we go. Oops, sorry. Ah, keeps cutting off. No, wait, hey, there we go. It's a little better. Right. So the rationals were still kind of like dit, 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 dit. There's a bunch of them, but there's even more irrational numbers, and those are what give you a nice, smooth, completed line. And that is what we call the real number line. All right. Okay. Now, uh, here's an interesting theorem, and I'm about to show you some really, really cool visualizations of the differences between rational numbers and irrational numbers. So here's an important theorem. A real number x is rational if and only if its decimal representation terminates or it has a finite decimal period which repeats infinitely. You probably heard this before back in grade school at some point, but if a number is rational and you tried to write out its decimal representation, then either that representation stops or it keeps going and going, but it's the same repeating pattern at some point. It could be like 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? So if you have a rational number, that has to happen. Or if that's happening with that number you're looking at, then it must be rational. Okay, so that's a property of rational numbers. We're going to explore the decimal system in more detail in 1.3. But how do you produce the decimal representation of a number? The Euclidean division algorithm. You just run the division algorithm. We're going to do an example in a moment here. Um, Now, this theorem equivalently yields that a number is irrational if and only if its decimal representation is infinite and not repeating. So every irrational number has an infinite decimal representation. That doesn't mean the number is infinity. That just means if you tried to write the number in a decimal form, you're going to need infinitely many digits to do it. And there's never going to be a point where afterward the digits repeat. Yeah, if the digits start repeating, no matter how far down, if you get down like a billion digits and then they start repeating forevermore, that's a rational number. But if they never repeat, they just kind of, there's never a repeating pattern, you've got an irrational number. Okay, so here's one I want you to try on your own. You might have to dig out some old skills. We'll review them in the activity. We're going to do this together, but I want you to try to find the decimal representation of 1/7 simply by dividing, okay? So think about it for a sec, okay? And now say something out loud to yourself about how you will try to do this division. Dust off those old skills. Okay, now try to work it out on your own, and then we'll do it together, and I'll show you a really cool visualization here. All right. Okay, so just as a little bit of a refresher, how do you divide 1 by 7? Well, if you remember, you add a bunch of decimal places. Oh my gosh, really got to fix this zooming issue. Okay, so you can zoom in with your eyes. You start with 1 and then you add a bunch of zero filled decimal places. And then you treat this as like a 10. How many times does 7 go into 10? It goes in there one time. And then you do 10 minus 7, you get 3. Bring down the 0, and then you repeat the algorithm. That's the division algorithm. How many times does 7 go into 30? It goes in there 4. So I put a 4 here. 4 times 7 is 28. I subtract. I get 2, bring down the 0, repeat the algorithm, dot, 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 dot. And what you'll find is that you get this period, or you get this sequence of digits, 1, 4, 2, 8, 5, 7. But then it's going to repeat, because if you notice down here, we end up with a 1 again, right? Well, if we end up with a 1 again here, and we bring down the next 0, we're going to have 10. And then it's how many times does 7 go into 10? Well, it goes in there one time. So then you would end up with 1. and you would do the subtraction, and then it just repeats, it loops, right? Okay, and then you keep going dot dot dot. So 1/7, the decimal representation of 1/7 is this. 142,857, 142,857, 142,857, on and on forever. Now, again, that doesn't mean the number is infinite, right? Like 1/7 is definitely not infinity. 1/7 is less than one, like it's a small number, but its decimal representation has infinitely many decimal places. That's all that's saying, right? So how do we denote that it's infinitely repeating? Well, usually we'll put a little bar over that part. We'll put a bar over the period, the sequence of digits that repeats over and over, okay? All right, now let's check out some cool pictures. So we're going to use decimals to get a unique look at rational versus irrational numbers. So pretend we're doing this. We're going to list the decimal representation of a number, say to 100,000 places or more, maybe a million places. And what we're going to do is we're going to assign each digit a color. So 0 will be red. That you can't even see me. Circle that in red. There you go. One is going to be orange, two is yellow, three is green, four is like a aquamarine, five is a light blue, six is a blue, seven is a dark blue, eight is purple, and nine is a pinkish purple. So those digits are going to correspond to those colors. And what we're going to do is we're going to list all the digits in a rectangular array going from the top left to the bottom right, just like you're reading a book. I had to think about that for a minute. Okay, so let's do 1/7. Let's take a look at 1/7. It would look like this. Okay, so now what I'm going to do is I'm going to zoom in a little bit here. I've got that the same thing pulled up. So this is 1/7, and what I'm going to do is zoom into the upper right corner here. Okay, so right up here at the very, very top. Hey, don't do that. We're just going to go in order. So it'd be like, what was it? Oh yeah, 1, 4, 2, 8, 7. Oh, sorry, I missed one. 1, 4, 2, 8, 5, 7. 1, 4, 2, 8, 5, 7. 1, 4, 2, 8, 5, 7. And it repeats. So you do all the way across the line. Each one of those pixels represents a digit. Okay, and then you get to this end, and then you go back to the left, just like you're reading a book. Okay, and then you go 1, 4, 2, 8, 5, 7. Okay, you got it? Got the idea? Okay, so that's what 1/7 looks like. Let's look at a couple other numbers. Let me zoom out again. Here we go. So that's 1/7. One of the things I want to point out is there's a pattern, right? There's like a repeating pattern here. Let's look at 1/8. 1/8 is a rational number. It's written as 1/8, right? So let's look at the picture. Oh my gosh, it's too red. Okay, so the decimal representation of 1/8 is 0.125, and then the rest is zeros. So do you see way up here in the corner? Let me zoom in. Let me zoom in. Zoom in. There we go. 125, and then the rest of the decimal representation is just zeros. Zero, 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 zero. That's why it's just a big red block, but the first three digits are 125, right? Rational number. Here's the repetition, okay? Oh, you can also find all of these pictures on Canvas. I uploaded them to the class Canvas page, so you can check them out there. Let's look at some other numbers. What about 1/3? What's the decimal representation of 1/3? Who knows it? Who knows it? It's 0.333333333. So what do you think the picture is going to look like? Solid green. 33333333333. There you go. Rational number for you. Kind of a boring rational number. All right, let's look at some others, but I wanted to pull them up here. Let's look at this crazy rational number. 576 over 107. This is what it looks like in decimal form. And its period is 53 digits. So it repeats every 53 digits. Let's take a look at it. That one's right here. Oh, wait, there you go. Phew. There it is. Pretty cool, huh? Oh, I zoomed in on this one. So this one is a million digits of that number. And again, you can see there's these like repeating patterns, right? Zoom in, there's a repetition. Can I even zoom in anymore? Will it let me? Wait. Wait a second. Should be able to zoom in more than that. There we go. Oh, just not doing it right. You see there's patterns here, right? There's a repeating pattern. Take a look at the blues. Take a look at these, maybe these orange rectangles here. So that's one of the characteristics of a rational number. It's got these repeating patterns, these repeating decimal periods. Here I just did a million digits. Even in this way, wait, maybe. Ugh. You can still see there's a pattern. Okay, let's do another one. Um, Oops, there we go. Let's do another one. Let's do 365 over 4789. So this one, actually, this one right here. We're going to do this one right here. There we go. So here's one where the period is 228 digits, but it's still a rational number. Let's take a look at it. Switch back. Okay, there. This one. So here's just 100,000 digits. But again, you see these like swooping patterns, right? That's characteristic of rational numbers. Pretty cool stuff, huh? Let's do another one. Next one is 12689 over 120,568. And that number has a period of length 6,456. Let's do this one. Woo. Okay, so again, it looks a little bit chaotic, but if you kind of squint a little bit or maybe stare really close, you can see that there's actually patterns, right? There's a repeating pattern. There's almost like a fuzzy, I can almost like see it. And it's like this pattern here repeating over and over again, characteristic of a rational number, right? Okay, now let's compare this to some irrational numbers like pi. What do you think pi will look like? Let's take a look. I've got pi pulled up right here. Here's pi. Almost looks like static, right? Just pure static at this point. Just pi. There you go. So you see there are no patterns. There's no like repeating pattern. I shouldn't say there's no patterns. There might be like a pattern in there for a little bit, but it doesn't go on forever. It changes at some point. That's what happens with irrational numbers. So this is the number pi, and you might be able to find some clusters of little patterns, but there's no continually repeating pattern that occurs after some point. None at all. How about square root of 2? That's another irrational number, kind of the first irrational number. There's the square root of 2. How about square root of 3? How about the number e? We're going to see the number e later on in chapter, what is it, chapter 4. We're going to see e in chapter 4. There's the number e. So you can see the difference between irrational and rational numbers visualized, just to give you some intuition again, right? All right. Now here's the crazy thing, I think. Computers cannot see irrational numbers because computers have to terminate their processes. Computers run algorithms, right? Well, they have to stop running the algorithm at some point. They can't keep going forever. But an irrational number has a forever long decimal representation. So computers cannot see these numbers at all. What they can see are finite approximations of these numbers. And that's exactly what you're looking at right here. I told the computer to stop after 1 million digits. It can definitely do that. Boom. It's right there. It has to stop though. So the number you're looking at here is not actually pi. It's a it's the first 1 million digits of the decimal representation of pi. Cool stuff, huh? Right? I think this is cool stuff. So I want you to keep that stuff in mind. And I also think maybe this is a good time to show this, right? Hopefully that's mind blowing a little bit to y'all. Um, I will also say if you want me to create any of these for you, if there's a rational number you want to see, just let me know and I can show you in class. It's just a quick computer code that will produce these for us, so it's not too hard. Okay. Last little bit here. Yep, last little bit, going on a little bit long here. This is a picture, a diagram of all of the different number sets. And by the end of this class, we're going to know about all of these number sets really, really well. This is actually my favorite version of this figure, this diagram, because it includes not only the real numbers, but also the complex numbers, which we'll study in chapter 3. So look at the bottom row to start. Just check this out for right now, okay? Um, Here's 0. Like I said, 0 sometimes is in the natural, sometimes it's not. This is the set of the natural numbers, the counting numbers, right? Positive whole numbers. And then here's the integers right here. Integers include the negatives. So the integers include the negative whole numbers. And you'll notice that again, the natural numbers are inside the integers. So this picture shows the inclusion relationship of the sets, right? And then here's the rational numbers. This whole thing here, that's the rational numbers. And again, you can see the inclusion relationship. The integers, I'm sorry, the natural numbers are in the integers. The integers are in the rational numbers. And then there's the real numbers. So the real numbers actually are this entire reddish strip at the bottom. Those are all of the real numbers. Now, one of the reasons I like this particular diagram is it distinguishes between what we call transcendental numbers and algebraic numbers. Okay, the difference between these two numbers is really, really important, and we're going to explore it when we get into chapter, oh geez, what is it? Chapter 5. No, chapter 3. Chapter 3 is when we start talking about them. Chapter 3. There's a difference between these algebraic numbers and these transcendental numbers, and that's why if you look at the title of our textbook for calculus, it's calculus and it says late transcendentals because transcendental numbers are very special in a certain sense. Okay. I also like this figure because it shows you that there's a separation of the rational numbers and the irrational numbers. So here it is. This is the rational numbers. This is the real numbers. And this little bit right here, maybe I shouldn't call it little, this gigantic bit right here, those are the irrational numbers. Irrational numbers. Again, we'll talk more about these types of number sets later on, especially once we get complex numbers, because there aren't just real numbers. There's another larger number set called the complex numbers, larger in a certain sense. I'll say quote unquote. The complex numbers include the number I, which is the square root of -1. We'll talk about it later. So all this rest of this part of the picture, we'll talk about that when we get to chapter 3. But on that note, let's play. So I hope you enjoyed this lecture too. I am really, really excited to work with you on these things, especially the stuff involving Euclid's division lemma and the division algorithm. Because if you ever had to learn about rational functions and like graphing rational functions, it's always very, very difficult. But if you remember Euclid's division lemma, we can make a lot of really good intuitive sense of what's going on with those rational functions. Just remember, every rational number can be written as an integer plus a fractional part. Well, maybe cutting to the chase a little bit, every rational function can be written as a polynomial plus a fractional part. All right, we'll get there. So thank you again. Ask me questions, and I will see you next time.